Okay, so today what I wanted to go through was PID controllers. So there'll be a little bit less actual coding today. And it's going to be a little bit more theory and drawing plots and stuff. But then we'll go through some of the actual code at the end. Today, my plan is just to do basically one session, because this is going to take more than an hour, but probably not quite 2 hours. So not enough time to switch over to a different topic. So does anyone want to talk about what they think of when they hear the words PID controller?
Better not tell that one, Luke.
Tell which one? Everyone knows that I'm just going to volunteer Alex if no one answers.
Fortunately, Alex just got here, so yes, you're more than welcome. Yes. Right, you're up, Alex.
I think of like, whoa, that's going really fast. It's like something that makes it smooth, but it like starts to like alligator, like it's like a.
Can you start with? Can you repeat that with fewer likes, please?
Okay, so like
No, that's wrong.
It's something that gets it to a set point with changing the variation, like it smooths it out.
It's PID controller,
Okay.
not the algorithm. It's a
Okay.
PID controller.
I think that, yeah, that's when I say controller, I mean algorithm.
Really?
Yes.
Mm-hmm. So technically the term controller refers to the math behind the algorithm, but I'm using them interchangeably.
See? I'm sure.
Okay, so as Alex said, a PID algorithm is one way to have the robot go from a certain state to another state. So go from one position to a set point position. So I'm going to go through all those terms and we'll sort of walk through it, and please feel free to stop me at any time. PID controllers do use calculus, but even though I think probably none of you have gotten to calculus yet, I don't anticipate that being a problem. So we can explain it and go through everything, except for Ms. Shanfield, who's gone through calculus.
Thank you.
Wait, I did beyond calculus.
No, you didn't.
Yes, I did with this word math.
So we should be able to go through it, and that shouldn't be a problem. But let me know if I'm using any terms that anyone isn't familiar with. Okay, so I'm going to do some drawing here. Hopefully the drawing won't look too bad. So let's see. Draw a line. Perfect. Let me do this. Okay. So throughout all of this, we're going to have two plots. So our first plot is, if I can select this. Yeah, I can. Okay. So our first plot here is of the, we'll call it the robot thingy. So this is something that we care about on the robot. It could be an arm, it could be an elevator, it could be the wheel speed, it could be the temperature of the robot, it could be really anything that we can measure and that we can change. And we're going to plot that as a function of time. And then our other plot is the, we'll call it the control signal that controls the thingy. So this could be the motor power. This could be, typically it's motor power for us, so I'll just leave it there. It's typically the motor power. And because it's typically the motor power, I'm gonna go ahead and set this as being on a range from -1 to 1, just because that's typically how we can, the minimum and maximum values that we can set the motor powers to. Oh, that's bad. Oops. See if I can. Okay. And then this one is also going to be as a function of time. And what's going to happen in all the situations we're going to discuss is there's going to be the robot thingy. So maybe the robot's elevator height is going to be at some position. So let me say that that is orange. So actually, I mean, learning all the drawing tools here. Oh, perfect. So the robot is at some position, and we want to take it and put it at some other position. So we've got here the goal position. This is also sometimes called the set point. And the wheel position, which I'm going to show in orange, so that's our star starting at time equals 0, is measured by something. So let me see if I can get this star icon here. So the star, which I'll just put off here with a note, is the current position of the robot thingy as measured by a sensor. And this is sometimes known as the process variable. But really, it's just a sensor reading of the thing that you're trying to control, which for us is often either the position of an arm or the speed of a wheel or anything like that. Are there any questions about what these two plots are going to represent and the process variable and the set point? Any questions on those? Okay, so here is our challenge. The robot is currently at this star position, and we need the robot to move itself, like move the arm, for example, or the elevator to the set point, to the goal position. And because matches are only 2.5 minutes, we'd actually like it to move there as quickly as possible, right? So, you know, if I draw here, you know, we would prefer it do that rather than that, right? We want, you know, this first curve here takes less time to get to the set point than this other option here, which takes more time in order for us to reach the same point. Does that make sense to everyone? Okay. So if we are, let's see here, just intuitively, if we're here, and I'm going to go ahead and also drop and say that to start out with, we're applying 0 power to that arm. What should we do to the power on the arm, sorry, the power on the arm, in order to move the arm position closer to the goal? Well, that's a question for anyone to answer. Okay, so Michael says increase the power. Okay, so let's do that. So what if we just turned it on at full power here? Okay. So when we turn on the power, this arm is going to start going up. Okay. What should happen when we get to the goal position? What should we do to the power once we get to the goal position? Okay, so Michael's answered apply minimum power to maintain the current position. That is correct. That's a little bit further ahead than I wanted to go just yet. So let's assume for a moment that the arm is not affected by gravity. So the arm weighs has zero weight, and so we don't need to apply any power in order to maintain a position. What should we do to the power once it reaches the set point?
Decrease?
Decrease. So if we were to decrease the power here, so say we just, decrease it below zero or just make it smaller?
Just make it smaller, I think, maybe.
So let's see what that would look like. So if we just decrease the power, so it's a little bit smaller. Again, if we were in a situation without gravity, we would still go up, but we would go up at a less slope, right? So we wouldn't go up as steeply. We'd keep going up if we just decrease the power. What are our other options?
To just stop it.
Okay.
But
So
I don't
if we
recommend doing that one.
Okay, so let me just stop it here, and then you can come back and you can answer why we don't want to just do that. So let's just stop it. If we were in a perfect world, stopping it, if everything was absolutely perfect, stopping it would work. So we could stop the power just as soon as we hit the set point, and we'd be happy. Now, the world is not perfect. So Lindsay, what are your thoughts on why maybe this isn't such a good idea?
Because then it would just start falling at a slower rate and it wouldn't be able to keep a linear line.
Okay, so certainly if there was gravity acting on the arm, or if there was friction in, a flywheel system or anything like that, that would happen. Let's remove the gravity and any friction for right now, and we'll get back to that later on. So what are some other problems that might happen with this system, even if there was no gravity and even if there was no friction? Do you think that we would be able to get the data from the sensor fast enough to stop the motor at exactly the right time? Okay, so someone says it would keep moving after we cut power. So okay, so even if we did sense it at exactly the right time and we cut the power here, maybe the system's got enough inertia that it keeps moving, so now we end up sort of stuck here. Okay, so I could see that as being a problem. So if we're now above the goal, what should we do to the power? Okay, Juliana says apply negative power. Okay, so let's apply full negative power because Max said he wanted the robot to move quickly. So now we're going to do something that looks like this, right? And we're probably going to overshoot it again. So this right here is called overshooting, where we go past the goal that we want. And if we kept doing this, we would get something that looks like this, right? me try and match that up a little bit. So that, and then that, and then that, right? So this is an option, and your process variable, the thing you're trying to move, is going to bounce back and forth around your goal that you're trying to get to. Now, this is actually a completely valid control scheme in some situations. So this actually has a name, this kind of algorithm, and it is called a bang controller, because it literally turns either full on or full off. Does anyone know what kind of system in your everyday life might use this kind of control system?
A drone.
Drone. I'm not sure that a drone would use it for anything. Not that I know of, anyways. How about the AC in your house? So when it's below a certain temperature, the AC turns off, and when it's above a certain temperature, the AC turns on. Usually, in most houses, the AC doesn't like change its power level. It's either on or off. And so it's implementing typically a version of a bang controller. And so your temperature is never exactly what you want it to be, right? It's always 1 or 2 degrees above or below the set point, but that's usually good enough. And so a lot of systems, particularly simple temperature controllers and things like ovens or AC units, do use a bang controller. And often in those cases, those are situations where you can't have where you can't have any values that are negative. So they're literally on or off, and those are the only 2 things that they can do. And they often can't go the other direction. Usually your AC unit doesn't immediately switch to heat if it gets a little bit too cold, for example. So this is totally reasonable for some things. I've used this on a robot for vision tracking before. It was a very simple robot, and it was pretty small, which is why I got away with it. But I used this to target on a target, and it works perfectly fine. So don't just because it's simple, don't necessarily assume that it can't do anything. Are there any questions about the bang controller where we just turn things on or off in order to try and get close to our goal? Okay. So what are some of the robot situations that we have where the bang controller probably is not good enough, where we don't want the robot to just bounce back and forth around the goal? Adam's on there. What do we need to use a more advanced controller for to move to a set point? We've got someone posted the shooter. Okay, we need a shooter. Someone also posted the elevator. Yep. Okay, so yeah, those are both excellent examples for places where we, just being close to the goal is probably not good enough for what we want to do. So fortunately, there are more advanced control schemes. In fact, there is usually it's within mechanical engineering. There's a whole subset of engineers called controls engineers who spend all of their time designing better controllers to get something state in a current position to a certain goal. And sort of one of the simplest that tends to be very effective is the PID controller. And in fact, it's so simple that the first ones were used on sailing boats, and they built the control algorithm mechanically. So they used mechanical gears in order to build a small mechanical computer that helped keep the ship steering straight. And it used a PID, it was a mechanical PID algorithm. So we're not gonna do it with gears, we're gonna do it in code, but it's the same principle. So let me see if I can erase some of this. Okay. That's a bang bang controller. The next thing that we have is the PID controller, and PID is actually an acronym. And I'll go through each one of those as we get to them. So before we talk about what PID stands for, why don't we just think about some things intuitively real quick. So if we've got our robot's position and you know, we are initially pretty far away from the goal, we start out with applying a pretty high power, right? Now, as we get closer to the goal, what we don't want to happen is we don't want to overshoot and go past the goal, right? So what could we do to the power in order to reduce the chances that we overshoot and go too far? Okay, so Michael says, gradually decrease the power. So if instead of having a constant power, as we got closer to the goal, we decrease the power. What that plot would look like is something like this. Oops. So I can draw more complicated shapes here. So as we get closer and closer to the goal, the power that we would apply would decrease. Does that make sense to everyone? Okay. So the way that we code this is we make the amount of power that we're applying proportional to the error between where we're trying to get to and where we are at any given point. So what we do, so if we can at any given point in time calculate the error. I'm going to call that E. Which is just going to be, let's see if I can do this here. It's just going to be E equals the the goal minus the current value. So right now the goal is larger than the current value, so the error is positive. And if we were, for whatever reason, to be above this line, with the position, the error would be negative because the goal would be smaller than the current value, and we have a negative error. Does that definition of the error make sense to everyone? Okay. And so when we say that the power, which I'm going to call that, capital P. So the power is equal to, is going to be, so let me type it out here first. So power is proportional to the error. And so what that looks like is power big P equals the error times some value. And we're going to call that K underscore little k underscore P. So this would be K subscript P. I just don't think I can type a subscript. No, I cannot. Okay. Okay. So this is just a number, and this is the error. And so, you know, if you could imagine that this is 5, this K underscore K sub P, then, you know, down here, the power that we're applying is the error times 5. And as we get closer and closer, that error decreases. So you're multiplying a smaller and smaller number by K sub P. And so you're applying less and less power as you get to here. And when the goal is exactly equal to the current value, you are multiplying 0 by whatever your K sub P is, and so the power you're outputting is equal to 0. Does this definition of the power being proportional to the error make sense to everyone? Or does anyone have any questions about it? Okay. So the P in PID stands for proportional. And some of you may have even used a proportional controller in Lego League for your line following code. I've seen a couple of teams do that. Again, proportional controllers can be very effective. In some situations, they can get you a curve that looks just like this, which can be very nice. Other times, they may be a little bit less well behaved. So, actually, let me get it on here. Okay, before I show you where this could break down, let me ask the question, does anyone know where on the robot we're using just a proportional controller on this year's robot? Alex, you might know the answer to this one.
Yeah, I was thinking, was it like auto and like the no, it was, or was it the shooter?
The shooter is using full PID.
Okay, so was it like driving auto or something?
So it's actually the swerve modules. So the azimuth motor on the swerve modules is only using a proportional controller. It's not using the rest of the PID.
Yep.
And it works pretty well. And as we go through this, I'll talk about why the proportional controller works well for the swerve modules, but not well for some of the other systems like the shooter or the elevator last year. But again, the sort of thing I want to emphasize is you should only use a controller as complicated as you need it. There are many situations where you can get away with a very simple controller in order to accomplish a given task. Okay, so now there are certainly tasks, many tasks, where the proportional, just the proportional controller is not good enough. So what tends to happen is in systems like, say, last year's elevator, or in this year's shooter speed, if you just had a proportional controller, what would end up happening is, you would slow down as you get closer to the goal. So it would look like this on the power curve. Okay. But typically, you still overshoot a little bit. And then you've got to wait for this to go a little bit negative. And then you'll overshoot again. And you'll come back up, and so that the power will then go positive again. And you'll sort of keep applying positive and negative power just like we were before. And now you're going to get this like oscillation. Is it smoother than with the bang bang controller? A lot smoother, and the overshoot should be less, but typically the oscillation still happens. Now, you could argue that if you chose the KP perfectly correctly, you could eliminate the oscillation. Typically, though, a KP that would result in no oscillation will also mean that it will take a very long time to get from your current position to your goal position. And for robots, particularly our robots, we really don't want to take that long amount of time in order to get from where we are to where we're going. And so we need another way, we need another tool in order to get rid of the oscillation that we have and try and minimize the amount of overshoot that we have. Okay. So before we talk about mathematically how we can reduce the overshoot, what I want you to think about is a physical system. So we've got proportional here. Okay. So we're looking at proportional. The way I want you to think about a proportional controller mechanically, you can actually think about all the parts of the PID system mechanically. So the proportional controller is a spring, right? Oh, a normal spring. It's not a constant force spring, but a normal just spring. As you, with a normal spring, if the goal is sort of the spring in its relaxed state, so if there was no force on it in either direction, that would be the goal of the spring. And as you pull the spring apart, the amount of force that you feel pushing back on you is actually proportional. It's the exact same equation as here to the distance that you're pulling the spring apart. So what happens when you release that spring, typically?
Compression and retraction.
Okay. And sometimes you get like a little bit of an oscillation, like a little bit of a bounce too, right? Does the spring though, does it bounce forever like this? Does it just bounce for, you know, an infinite amount of time, or does it eventually stabilize at its normal resting position?
It eventually stabilizes to the point where we can't tell that it's moving anymore.
Okay. So what's making it, why does it stabilize? Why doesn't it keep bouncing back and forth?
Physics.
Physics, okay. You're not wrong, good answer. Any thoughts on what specifically in physics is making it eventually stop moving? Okay, so Michael's posted in the chat friction. Absolutely correct. So there are frictional forces, whether it's in the metal itself, or, I mean, you could even think of air resistance. I don't know which impact that has on the spring, but that could be there. So there's some amount of friction in the whole system that is eventually dampening out the oscillation. What we need is a software way of dampening out the oscillation. And the way that this is typically explained on the mechanical side is we need what's called a damper. And the thing that is closest to a mathematical damper is cars have these. They're basically plungers in a tube in like a cylinder with some sort of fluid in it. And you can imagine that if you tried to move the plunger within the tube with liquid, you're going to get resistance. Do you think that the resistance of pulling something through a liquid is going to be the same all the time, or are there things that you can do to how you pull it that make the resistance more or less? So think about it this way. Is it easy? You think it'd be easier or harder to move something through water if you moved it slowly or if you moved it quickly? Alex, what do you think?
Well, at first I said fast, and then I was like, well, slowly, and then I didn't know.
So in
Wait.
most fluids, oh, go ahead.
Wouldn't it be slow?
So in most fluids,
Because,
oh, go ahead, Lindsay.
never mind, it's probably wrong. It's a bad analogy.
Okay. So in most fluids, the amount of resistance that you get is more the faster that you move. There are some very cool special fluids where that is reversed, but we won't talk about those today. But in most cases, the faster you try and move something through a fluid, the more resistance you feel. And in fact, what we find is that in a mathematically perfect damper, we'll call it resistance, which is the same as the reverse power in our analogy, is proportional to the velocity. Proportional to the velocity. So you'd have another thing where you'd have a power component that is equal to, I'm going to call it the velocity v, and times some coefficient k sub d. And I'll talk about why it's d in a second. That k sub d for us is going to be a value that we type in. In physics in the real world, that might be something that you experimentally determine. So if you're moving something through a fluid, that k sub d is going to be dependent upon the fluid that you're moving the object through, and it's going to be dependent upon the shape of the object that you're trying to move to the fluid. But it's a real value that you could experimentally calculate. For us, we're going to type it in, and when we're looking at this, let me ask this question here. So let's just pretend for a second that this portion of the line, this portion of the curve is a straight line, okay? Perfectly straight line. Does anyone know how we would calculate the velocity of the line? So how about this? Let me ask this question. Okay, so Michael and Juliana say rise over run for calculating the slope. So that's correct. Let me draw what I was going to draw here in a second so everyone can catch up. Excuse me, catch up to that. So we've got two lines here. This line and this line, and we'll call that line A and line B. which of these two lines has a higher velocity? And someone other than Michael and Juliana.
A.
What do you say, Alex?
A.
A, yep, correct. So the way we can calculate the line, the velocity of this line here is by looking at the slope of that line. So a steeper slope means that you're getting from, this location to some other location faster, so you're going at a higher velocity. The analogy, or sorry, I lost my train of thought for a second. What did I want to say next? I've now forgotten. So I'll just type here, the velocity of the line is also known as the slope, and it's also known as the derivative. And the term derivative is where we get the D in PID from. Derivative. And it literally means that the part of the power, in order to add resistance, so let me do this. Oh, this is gonna be kind of annoying. Can't like edit the, oh, I can edit it, okay. So this is power underscore proportional, and this is power underscore derivative. And so the total power here that we're going to want to apply is going to be some combination of the power that we get from how far away we are from the goal, which is the proportional power, plus power from that's related to the velocity. So power D. Okay. Let's see here. Okay. Okay. Now, let's see what I want to say here. Are there any questions on the idea, just the concept, that in order to sort of incorporate some sort of resistance, we're going to want to take the amount of power that we have based on how far away, based on the proportionality of the error, and combine it with what we're going to talk about with the derivative. Are there any questions up to this point? Okay. So let me reset here a little bit. And okay. So before I go into the math here anymore, let me show you what the plot looks like if we've got a derivative term incorporated into this. So if we take our same problem and instead of just having the P term, we also have a derivative term. When we start out, our Sorry, I had to explain one more thing first before I go into that. So move that off to the side. When we're looking at how we actually calculate P sub D, the velocity that we're actually looking at is the velocity of the error. So this is how fast is the error changing times K sub D. Stick that right there. So does everyone understand what I mean by how fast is the error changing? Right. So when we first start out, the error is not decreasing very much, is not decreasing very quickly. Now, as we get closer and closer to our goal, the error is decreasing. And it's decreasing faster and faster. So if the error is decreasing, this statement that's in parentheses of how fast is the error changing, is it positive or negative? If, let me write this here. So if, you know, if E1 here, let's see. Oh, this is, I really wish I had a whiteboard. That's E1, and this is E2. Okay, and so E2 is less than E1. Do you think that is the velocity of the error, how fast the error is changing, is it positive or negative in this scenario? So Michael says positive.
Isn't it?
Say that, Lindsay?
Is it negative going positive?
It is negative going positive. So, you know, if we were to cross this line, we would start being positive. So if right here, E2 is less than E1, then if we're calculating, it's a little bit more complicated than this. I'll talk about that more at the end. But if our velocity is, I'm going to say, let me see if I can do this here, approximately equal to E2 minus E1. Oops. Then at this point, this is a negative value, right? Does everyone see that it would be negative? Okay. So if it's negative, and so if it's negative, this term, oh my goodness, this term here in the power is going to be negative plus a positive that we're getting from the proportional. So this one right now is positive. This one right now is negative. So what it's saying is that if the error is decreasing very quickly, we're going to back off on the power sum that the proportional controller is giving us. So instead of overshooting this, we are going to intelligently decrease the power a little bit more sharply as we get really close, and only overshoot a little bit. And then instead of bouncing back and forth forever, as we see the error changing, we will eventually dampen out and die down. So the velocity, if this was what we had before with the power going down, now all of a sudden it sort of goes down a little bit faster, and then we're able to sort of dampen this signal also, the power also will dampen down with this. Does everyone see how applying this resistance as we see ourselves sort of, you know, if you're the elevator, and all of a sudden you're moving great, and then you basically see that you're getting close to your goal, and you're still going really fast. Like you're going really fast. You're worried that you're going to overshoot, so you back up on the power some more, and so that you don't overshoot as much. And then when you're right there bouncing around, you start to sort of clamp down on how much power you use, and so you settle a little bit. Does everyone have any questions on how that physically would work? Okay, so what the derivative is allowing you to do at this point is it's allowing you to start out with a very steep slope, which is good. So you can make your KP term here very large and get to your goal very quickly, and that's okay, because once you start to get close, the KD term, this PD term, is going to start getting negative, and it's going to clamp down on your power. And so it's going to all of a sudden drive you down and keep you from overshooting too much. And so what that allows you to do, is get to your goal while being what we call stable much faster than if we just had the P term, right? Again, if we wanted to have just a P term and just sort of end up at our goal, our curve would look like this, and it would take us much longer to get to our goal than if we had the P term and then we had the D term on top of it, keeping us from overshooting too much. Are there any questions on sort of the comparison between the plot with just the P term to get to the goal, and then the P term with also the derivative term as well? Okay, so excuse me. Let's talk about the swerve modules real quick. Why do you guys think that we might be able to get away with just a P term on the swerve modules and not have to include a derivative term? Adam, what do you think? You built the modules. Why do you think we might be able to get away with just a proportional term? Good question. So Michael asks, do I mean the driving wheel or the wheel turning it? I mean the wheel that rotates it angularly, so the azimuth motor that moves it from angle to angle. And while you guys are thinking about that, remember what the derivative term is pretending to be, right? The derivative term is pretending to be resistance or friction. So Juliana says the swerve modules have a lot of intrinsic friction. And Lindsay says, is it because nothing's perfect and there will always be outside forces? Both of those answers are perfectly correct. So it turns out that the robot's kind of heavy and the wheels kind of have a lot of traction. And so when the robot's on the ground, there is a significant amount of friction between the wheels trying to rotate and a significant amount of friction when the wheels are trying to rotate and change their angle. And real world springiness and real world resistance count here too. You know, this is the portion that we are adding on to the real world physics with the motor. The real world physics is still happening. And so there is enough real world derivative basically that, excuse me, that we don't need to put in a software derivative in order to keep the wheels from bouncing around. So one thing that you might have noticed is that when the robot is up on the cart and we move the wheels to a set point, you will actually see a little bit of jiggle, they'll bounce around. Whereas if they're on the, when the robot's on the ground, you don't see that jiggle, or at least not as much of a jiggle. Because when it's up on the cart, we've tuned the robot so that the wheels perform well when it's on the ground. And when it's up on the cart, it has much, much less friction than when it's on the ground. Does anyone have any questions about about the sort of the real world friction and how the swerve module behaves? Okay. So you may have noticed that there's still another term here in the PID algorithm, PID controller. That's because there are still more problems that we need to fix. So in most real systems, there is a certain threshold of power that is required in order to make the robot move, or make whatever mechanism move. So what tends to happen is if you just have a P and a D term, you'll overshoot a little bit and you'll dampen out. But unfortunately for you, you dampen out not at the goal you want, but a little bit above or a little bit below the goal that you're trying to get to. Because if you look at this here, what you find out is the following. So in this case, we'll call this E. So I'm going to call this ESSE. The SSE stands for, let me see if I can put that down here. SSE stands for steady state error. This is the error that you have after the system has stabilized and existed in that state for a long time. And so if this steady state error is pretty small, then when you calculate, right, so if you've got, let's see if I can, P total, this equals K underscore P times ESSE plus K underscore D times, I'm just going to say the derivative of the error. Okay. So we'll start with this. If if the steady state error is really small, how big do you think that this P underscore P term is going to be right here? Right, so if we're looking at, this is just some value. I'm just going to throw in this is just some value, and this is small. How big do you think that this is going to be? Okay, Michael says very small. Yep. So I'm just I'll finish this line up here in a second, but I'm just going to say this is small. Okay. And then what is the slope of this line here? Or sorry, if we've stabilized, what is the slope of this line right here? Okay. Also very small, right? Or small. It's you know, kind of, you know, close to zero. And so this term is also going to be small. Okay. So we have a very small power right now. And maybe the elevator is 2 or 3 inches away from where it needs to be, but maybe on the robot, this equals 0.05 power, 5% power in the motors. In many cases, this may not be enough to actually move the mechanism. I say the thingy, right? And so you're going to end up getting stuck here, and you're going to be far enough away that, you can measure it, you know that you're wrong, but close enough that the amount of power that your algorithm is telling it to send to the motors is still not enough in order to make the mechanism move. Does anyone have any questions about that problem? Okay. So what would be a solution if you were the robot? What would you do in the situation in order to get to your set point? Apply a constant negative power. So Juliana says apply a constant negative power. So let's see. So if we just always had, if we said, once it's stabilized, so say, we had, let me see if I can draw this here. So this looks something. This power curve looks something like this or something like that, right? And then Juliana suggests that we could basically shift that down a little bit and always be applying some negative power. And you're right, eventually that would start to shift us down. But that's an option. What might tell you how much negative power you should be applying and when to turn on and off negative power? Because eventually you want to go back to 0, right? So that when you get to the set point, you do want to be at this level at the set point. Okay, so Joanna says when the error stays steady for a long time, but isn't 0, apply the negative power. Okay, so that's completely valid. You can, one of the ways that people do this, because it's sort of hard for code to answer the question, stays steady for a long time. It's sort of a tough question to answer. What we can do is make it so that we have a power term. See if I can write this here. We're going to have a power term, p sub I, which I'll explain the I in a second, which has some coefficient ki, so it's proportional to the error. I'll say the amount of error over a period of time. So we can essentially count how much error we've had over a given time range and make this term increase, and this term will get thrown in right here with the p total, p sub I. And so when we're starting out, the error is constantly changing. So when we start out, the error is constantly changing. But when we start to get this error here, let's see if I can erase this too. When we sort of got the steady error, the power, as we've had this error for longer, the amount of negative power that we apply gets more and more. And so we drives us down, and then the error starts to decrease. And so we've had less error over the amount of time that we're looking for. And so we come back to 0. I'm sorry, these are sort of out of sync, but this endpoint here is matching up with this endpoint here. And so you have an amount of power that you are applying to your total power that is related to how bad your error is and how much time you've had that error for. So, you know, it's bad to have a big error, but what really matters is that you've had that error for a long time. So this will take effect either when you're really, really wrong, or when you've been a little bit wrong, but for a long period of time. And so you can sort of think of that as, and this is going to be a very loose definition. We're going to call this P sub I is proportional to the error times the time that we've had that error for. And it looks like, pardon the use of the word time, but it looks like we'll have time today to go through what the actual mathematical definition of that is. But just conceptually, this term is now proportional to how bad the error is and how long we've had that error for. And the term for the math part of this is integral, and that's where the I comes from in the PID term. Does anyone have questions about the conceptually what the I term does and what it contributes to the behavior of the system? Okay, so pop quiz time. Oh wait, someone asked, before we get to that, at the beginning, wouldn't the I be thrown in with the P when we have a large error, or does the D take care of that? That is an excellent question. Yes, if the original error is very large, then it is possible for the integral term to be very large as well. And this could dramatically skew the results here. Like it can skew the amount of power that you're sending to the motor. This is a problem that's often referred to as integral windup. This can also happen not just when the error is large, but if it takes you a long time just normally to get from one point to the other one, like even if that's how the system is supposed to behave, you can get what's called integral windup, where you end up with a very large integral term. And there are a lot of approaches to mitigating, to making it so that the integral term doesn't do that. The two most common is that instead of looking at all time, so if this is 0 time and this is the current time here, looking at all time would be, looking at this entire, looking at this entire amount of time. You could instead look at only a short window of time. That will limit how large the integral term can get. And then the other option is to turn off the integral term unless your error is within a certain range. So you could basically not turn on the integral term until the value is somewhere in here. So the integral term would not exist in this section of the curve, and the integral term would only turn on for these sections of the curve. So those are sort of your two most typical things. So I'll put that down here. Solved with time window, or only turn on PI when E is small-ish. Does that answer that question, Juliana? So asking in solution 2, would we have this problem as well? You could, and you could have this problem in solution 1 too. This is where tuning of the PID, which I'll talk about in a little bit, really becomes key. There's always a trade-off. You're going to have to find a time window that works, and or a minimum or maximum E value that works for your given system. There's not unfortunately, a end-all be-all solution to this. And I'll talk some more in tuning about how we can mitigate that problem. Are there any other questions about the integral windup issue and why we need to have sometimes solutions for limiting how the integral is allowed to come into play with the overall power that we're sending to the device? Okay. So my question for you is, and I'm just going to start volunteering people if people don't volunteer themselves. Can someone explain what the proportional term does in the PID algorithm? So Juliana said, proportional is the rate we increase power initially. Certainly proportional is the term that is most dominant at the beginning of us moving towards our goal. More explicitly, proportional is the component of the total power that is directly proportional to the error between our goal and our current position. Let's see. Lindsay is asking about, Lindsay, can you clarify your question on the bang bang controller? I don't know if anyone else can see that question. We can come back to that. Oh, wait. Oh, okay. I see. Okay, yeah. So it is true that the proportional part is one of the things that differentiates the PID algorithm from a bang-bang controller. Instead of always applying the same power when we're not at our set point, the amount of power that we apply is proportional to our distance from that set point. Can someone else, other than Juliana, talk about what the derivative term physically does in the algorithm? So Amelie says the derivative is the dampener. It is proportional to the velocity and prevents the power from speeding up too fast. Exactly correct. Can someone other than Juliana and Amelie answer what the integral does physically in the system. All right, Alex, you're up. You know I'm going to pick on you.
It gives it the little boost of power, and it like makes it get rid of the error. Like once it's smoothed out, it like pushes it up to where it needs to go.
Yep, exactly. And Lindsay actually also answered that at the same time, saying, doesn't it give it a start point? I would say that more like what Alex said, it allows you to fix your endpoint. So you have some endpoint that isn't exactly what you want. So it fixes the endpoint so that the endpoint does end up being the set point that you want. Are there any questions on the PID portion of this before I burst everyone's bubble and tell you that gravity exists? Okay, so this next bit here, we'll go back to something that Lindsay and I think one other person also brought up at the very beginning of this, at the very beginning of today. So if we're looking at this as the an elevator, like if our specific application is an elevator, and let's see here, let me erase this. And again, if we start here and we have our perfect PID controller, we're going to, oops, draw here. We're going to go up, overshoot maybe a little bit, oscillate a little bit, but dampen out pretty quickly. And then we'll take it back down with the integral. Okay, so we're going to end up with a curve that kind of looks like that. And our plot of power would look something like, maybe something like that, and then that, and then we've got to have a little bit more negative here, just so that we get rid of the error. And again, I'm sorry that this doesn't quite line up, but you know, this point here is the same as this point. I'm just bad at lining things up with the mouse. So if this is an elevator on last year's robot, what power are we giving to the elevator right now when we're at our set point? So Michael says 0 power. What happens to the elevator when we give it 0 power and it's up at some height? So Michael says Michael and Lindsay both say it falls. Exactly correct. So great, we've gotten to our set point and everything is fantastic. We're happy. We turn off the motor because we don't need to move anymore. And all of a sudden, we were nice and happy. All of a sudden, the elevator falls again. And now we're back. We have to, now the PID, you know, the PID controller is not turned off, right? It's still looking. It still sees, oh, the error's gotten bad again. Let me do the same thing. So it's going to do this exact same thing again, be steady, and then it's going to fall again, right? So the PID is going to try and catch it from falling. And in a real system, it doesn't quite necessarily have to look this bad. Typically what ends up happening is something that looks like this, and you just sort of always have these weird drops. And so you're always oscillating a little bit back and forth as the PID controller gets close to giving it very little power, and then you get back to your set point and you come back down and it shuts off and the arm falls. So this is a pretty classic problem. It exists not just with things like elevators, but we have this problem on the shooter wheels this year. We don't have gravity on the shooter wheels, what we do have is friction. So, you know, once we get to the speed that we want to be at with the shooter wheels, if we just turn off power to the motors, those shooter wheels are going to start slowing back down again. So in order to improve what we call the stability of the system, we add to the power here not just the PID term, but another term called a feed forward term. I'm just going to call it, the convention the same, P sub feed forward. And the reason that we call it a feed forward comes from some terminology in, I guess I should have explained this. So a PID controller, let's see if I can get this. A PID controller is a feedback controller, and so is a bang bang controller. They're both feedback controllers. The feedback wording means that this controller relies on getting feedback from a sensor in real time in order to know what power to output. The feed forward terminology means that this power is predetermined based on a physical model of the system. So forgetting the elevator for a second, if we were to think about the shooter wheels this year, we know that we need more power in order to make the wheels spin faster. And if we took a whole bunch of, we made a whole bunch of experiments, we could probably find the quote unquote correct power to apply to the shooter wheels in order to get them to be about the speed that we want them to be. So we would test a whole bunch of powers, see what speeds those are at, and then depending on what speed we'd want, we would apply the correct motor power. This would be our model of the system. This would be our best guess or our best description of how that system behaves in real life. Now, this feed-forward model isn't perfect, right? It doesn't incorporate everything. If the battery sags a little bit, if the battery voltage drops, or if we shoot a ball, those things aren't accounted for in the model. And so we need the PID controller then to sort of sit on top of the feed-forward controller in order to correct for those disturbances. And that's exactly what the PID is best at. It's correcting for disturbances and things that we don't expect to happen or we don't predict will happen. But the stability of the system really relies on us having a good model for how that system behaves. And the simplest model that you can have is the model that we had for the elevator last year, where we did a whole bunch of tests and found the power that we have to apply to the motors in order to hold the elevator completely stationary. So what we ended up doing was shifting up. Let's see if I can select those here. Shifting up this curve so that no matter what, even when we stopped trying to change position, we were always applying some minimum power to counteract gravity. And so what you essentially end up with is this term, this feed-forward term is responsible for things that you can predict, right? We know how heavy the elevator is. We know how that system is going to behave. And then this term, all three of these PID terms are responsible for unpredictable things like how the battery voltage is going to drop, or you know, in addition to the unpredictable things, these are also responsible for moving you between heights, right? If we've just got this minimum power, that's just going to hold us in place. So, you know, if we want to go up to a higher height, we're going to need to apply some sort of positive power in addition to this minimum power. And if we want to go to a lower height, we need to apply some sort of negative power relative to the minimum power. So the PID is doing the job of moving us from position to position, and the feed-forward controller is dealing with holding us at that position once we get there. Are there any questions about what the feed-forward controller is supposed to be doing in these situations? Okay, so the feed-forward in most of the applications that we do is pretty simple. It's usually just a constant number. So, you know, if it took us 30% power to keep the elevator held at a keep the elevator held up, then P feed forward is going to be plus 0.3, and it's going to be just that value always. Now, you can start to build up more complex models. You could do a whole bunch of experiments where you look at how the battery voltage affects what power you need to apply to the elevator, and you could read in with a sensor what the battery voltage is and actually modify your feed forward value based on your battery voltage. And so now the PID has to do even less work. You could make a model where, you know, if you had picked up a cargo or a hatch, that adds a little bit of extra weight to the robot, so to the elevator. So if you knew you were holding those items, you would go ahead and increase your feed forward power. Again, your sort of goal is to reduce the amount of work that your PID controller has to do to the bare minimum. And you know, if the world was perfect, you do everything with the feed forward controller. But since the world isn't perfect, what you end up with is an approximation of a perfect feed forward, approximation of a feed forward controller, and then you use the PID to take care of all the things that you didn't get right with your feed forward controller. Does anyone have any questions on anything that we've talked about up to this point? After this, I'm going to go into how you would actually tune a PID controller. And then if we still have time, I'll talk about how to calculate the derivative and the integral in order to actually implement the algorithm. No questions at all, huh? Everyone's got this completely down? Okay. So, all of these P terms that are going into the total P are based off of some measured value, whether that's the error or the derivative of the error or the integral of the error, but they're all multiplied by some coefficient, either Kp, Kd, Ki, and then also there's a feed forward term. And the process of tuning the PID algorithm in order to make it behave nicely can be, I don't want to say it can be difficult. It can be difficult if things happen in the wrong order. And it can certainly be very stressful because when the PID algorithm isn't tuned, the robot is bouncing all around. And whether that's the shooter or the elevator, that can be kind of scary, and it can also damage the robot. So, you know, there's always some amount of anxiety with tuning any PID loop. But if you go in the order I'm going to talk about, you'll have a lot higher chances of succeeding quickly and reducing the chances that something goes really wrong or something gets damaged on the robot. So let me see what I can do here. So let me erase, let me keep this. And I'm going to go ahead and I wish I could like make a new page. See, we don't need this anymore or that. We don't need that. I'm just going to work over here in this corner and try and keep the rest of this up. So my general suggestion for tuning this algorithm is the following. First thing that you should do is figure out your feed forward value. So in the case of the elevator, this would be determining what power is required to hold the elevator at a constant height. In the case of the shooter wheels this year, this would be determining so for the shooter, it's a little bit different. So if it's the elevator, so if this is the elevator, this is a constant value. So this would be power to hold up elevator. With the shooter this year, this is actually, what you're finding is, and this is KF, so this is just equals K sub F, so K sub feed forward. With the shooter, this is power to maintain speed, like shooter speed. I'll call it shooter speed. And this is a function. So let's see if I can have it over. There we go. And that is K sub F times the goal speed. So the model that, in this case, we're using NEO. So the model that Rev came up with is that we know that we need more power in order to spin the wheels faster. So the feed forward portion of this is some coefficient times whatever our goal speed is. So at higher goal speeds, it's going to be more power, and at lower goal speeds, it'll be less power. This is not a perfect model by any means for what's going on, and if we had full control over the system, I would definitely do a different model in this, but it's an approximation that's reasonable. And so in the tuning process, then you'd be finding this KF value. Basically, when you're doing this first step, you want to make sure that it's like a good value, but it does not have to be perfect. Don't try and make it perfect, because the reality is, as you're tuning all of this, your battery's changing, a new battery's going to go in, that's going to change things. Don't try and make it perfect with just the feed forward portion. Getting it perfect is what you're going to do with the PID portion. But it needs to be a good guess, but it does not need to be perfect. Any questions on the feed forward portion of this here, and maybe the differences between the elevator and the shooter? Okay. So the next thing, I guess I should have also said, you should always, with all these values that you're trying to determine, whether it's KF or any of the ones I'm going to talk about in a second, you should always start really, really small with the values you're typing in, and then work your way up. So there are ways to pre-estimate what the value should be. If anyone's interested, we can go into what that looks like. Usually that's not necessary for what we do, and my suggestion is that you just start with a really small value and work your way up until you start seeing changes, and then you'll get a pretty quick sense of how much you can change the value and what kind of impact that has on the system. So once you've got your feed forward figured out. The next one I suggest you work on is the proportional. And basically, I would increase KP until the system starts to oscillate steadily. And what I mean by steadily is it should oscillate like this, where the values aren't really getting bigger or smaller. It would be an unsteady oscillation. What you don't want is where it starts oscillating small and then starts oscillating really, really big. That can also happen. So you don't want the KP to be that bad, but you do want the KP to have some oscillation. If you tune the KP value so that you don't have any oscillation, I mean, congratulations, like that could be good, but you're taking more time to get to your set point. And our whole goal here is to get from our current position to our set point as quickly as possible. And so my recommendation is that you tune it so you get a steady oscillation when you just have the KP term. Okay, and then once you've got the KP term set up so you've got that steady oscillation, you should increase the KD until the oscillation dampens out. So, you started with this, and what you want to do is keep turning up KD until you get this. And ideally, you'd want to keep turning up KD until it looks something like this, with maybe just one or no oscillations at all. Now, what can happen is you don't want to go too high, but be careful not to go too high. If your derivative term, I'm sorry, Michael was asking, if we don't get that, does that mean the P is too high? Sorry, I don't remember what I was talking about. I didn't see the message come by. So I don't remember what I was talking about. Michael and Juliana, can you ask that question again real quick? If we cannot get the oscillations to flatten, does that mean that we should decrease P? Yes, so that's another good point. Let me finish with the derivative, and I'll circle back to that real quick. So if you keep increasing, if you're still trying to get rid of the oscillations, and your strategy is I'm going to keep increasing D, at some point what happens is you start getting what we call clamping. So the algorithm sees that the error is decreasing really quickly, and all of a sudden the derivative term really kicks in, and you start to look like this, where it's aggressively trying to slow the power, trying to slow the rate at which you're approaching the goal by running the power really negative. And so if you get to this point, you really can't increase the derivative term any higher. So Juliana asks if we've increased derivative as high as we can possibly get to it, and we see, because we see clamping, and we still have oscillations that we can't get rid of, what do we do? At that point, you are going to need to decrease your KP term until you get rid of your the oscillation. So you're going to have to sacrifice some speed at getting to your goal in order for stability. So you may have to do this instead, So you get at least a nice damp response. And so you won't get to your goal as fast, but you won't get the oscillation. So that would sort of be the trade-off that you have to make. Does anyone have any questions about the trade-offs between and how we tune KP and KD? Okay, so once you've tuned both of these values, I would now look at tuning KI. And when you tune KI, you're going to have to do some things in parallel, which is a little bit frustrating. So I would increase KI until you get rid of any steady state error, right? So what we've got at this point is a plot that looks like this. And we just got, this steady state error here. We would increase KI until we get rid of this. Now, as you're doing this, you may end up with integral windup where you start to get really strange behaviors when you're very far away from the goal. And typically those behaviors manifest as a plot that would look like this. So you'll have a nice P here, and then all of a sudden, your power will go way up and you'll start increasing really fast. And now the thing that you had tuned to not overshoot much is going to really overshoot. And it'll do this, and then maybe it'll do that. And now you're overshooting with this. So we'll sort of get a plot where you've got a steady increase, and then basically your integral winds up and gets really significant in this equation here for the total power. And all of a sudden, you're increasing really quickly and you're going to overshoot again. In this situation, either you're going to need to decrease KI, which you may not be able to do, right? You may have to have that large KI in order for you to get rid of your steady state error. But if you can't decrease your KI anymore, now you're going to need for this problem, so you get rid of any steady state error. But if you, let me do this. If there's overshooting, now you need to tune your, we'll call it the PI on window. So this is the error must be smaller than this for the PI term to turn on, right? That allows you to ignore the PI term when you're sitting down here in this part of the curve, and only deal with it when you're very close to the goal. The other problem that you could end up having is you could end up with, as you're turning up the KI, is, let's see. You could get to a pretty happy place, not much oscillation, and then instead of doing a nice smooth come back to here, you end up with something that looks like this, where all of a sudden the integral gets so large that it drives you down well past what your goal is. Or even worse, if you spent a long time getting up to here, you're counting error that you've had this whole period of time. And so as you start to stabilize, you then go like that, because it still remembers that you spent a long time below your set point. And sort of still has that memory stored in how much power should be in the integral. And so in that scenario, where you've got, I don't know, I'll call it sudden destabilization, that's when you need to tune the time window. So this is this option number one, where it's the amount of time that you calculate PI for. And then the third thing that you can do as an option for both of these is you can go back and tweak your feed forward controller. Go back and tweak K sub F. That's another way that you can try and help with this problem as well. Are there any questions on the tuning process? Okay. So what I'd love to do is at some point, if we can get a robot, I'd love to be able to show you guys what the plots really look like and really go through the tuning process, because it is a very hands-on thing. Working with these algorithms in a physical piece of hardware takes practice, and it takes, the practice is not just to know what to do, but the confidence that you're not just going to immediately break everything, and you just gotta very methodically go through stuff and be very careful, but be confident in yourself to let the robot oscillate so that you can get the data that you need and see the plots that you need to see in order to understand the behavior.